We're looking now in this tape at techniques of anti-differentiation. And these are truly techniques because there's no really one method. There are very many methods for anti-differentiation. Some of the things that you already know, however, are the following. The antiderivative of x to the n with respect to x is x to the n plus 1 over n plus 1 plus any constant. Right? This is for n not equal to minus 1. And this generalizes, for that matter, to if we've got f prime of x to the nth power with respect to x, where n is not equal to minus 1, then the antiderivative of this, well, a good guess would be f of x to the n plus 1. The derivative of that is going to be f of x to the n times f prime of x times n plus 1, so that this divided by n plus 1 is the correct derivative here. When n is equal to minus 1 now, we know that the derivative of f prime of x over f of x with respect to x is log absolute f of x plus any constant. And there are some other formulas that we know at this point in time. Namely, the antiderivative of e to the x with respect to x is e to the x. The antiderivative of sine x with respect to x is cosine x, is minus cosine x plus any constant, of course, here. And some other formulas here. For example, the antiderivative of secant squared of x with respect to x is tangent x. So any function we know the derivative of, we now know the antiderivative. We also know the antiderivative of that derivative. One other thing that you know at this point is substitution, and that's based on the chain rule. That's to say, that if we have f of g of x, the derivative of this is f prime of g of x times g prime of x. So we should have that the antiderivative of f prime of g of x times g prime of x with respect to x is this. Clearly it is. But now, with substitution, what you want to do is you want to ask the following type of question. If I let u be equal to g of x in here, then du, the differential, if you want, is g prime of x dx. Is it possible to change this over and write this as the antiderivative of f prime at u, g of x, g prime of x dx is du. Well, the antiderivative of f prime of u with respect to u is f of u, and since u was g of x, we get f of g of x, so plus any constant here, of course, throughout. And the fact that the answer is f of g of x indicates that you can make this substitution, letting u be g of x, du be g prime of x dx, and if you do that, change everything over here to u's from x's, you end up with the correct answer. That's to say, you end up with f of g of x when there was a composition involved. That's substitution involves guessing that there's a composition involved. Let's take a look at a couple of examples of this as a sort of a refresher. Suppose we have x e to the x squared with respect to x, and we want an antiderivative. Right? Well, if we let u be equal to x squared and du equals 2x dx, then we have here that this is equal to e to the u. Well, we need 2x dx for du, or x dx is du over 2. So 1/2 du, and the half can come out of the integral. And now that this then becomes 1/2, the antiderivative of e to the u is e to the u, so it's going to be e to the u, which was x squared, plus any constant. That's one thing to note here is that the only two formal rules are the antiderivative of a constant times a function, so constant times the antiderivative, and the antiderivative of the sum of two functions is the sum of the two antiderivatives. Everything else is generally not legal to do. Let's try another integration by substitution here. So this is substitution. Let's say 2x square root x minus 1 dx. Here you don't like to see this x minus 1 here, so if we let u equal x minus 1, du is equal to dx, and in this case, if u is x minus 1, then x is equal to u plus 1, and this becomes 2 antiderivative, x becomes u plus 1, and now we've got square root of u du. Now in this case here we can multiply this out and get antiderivative of 2u to the 3 halves plus 2u to the 1 half du. Now the antiderivative is going to be equal to 2u to the e to the 5 halves, 1 higher power over 5 halves, plus 2u to the 3 halves over 3 halves. And now u was x minus 1. So x minus 1, and of course plus any constant. So the antiderivative is given by the bottom line here. 2x minus 1 to the 5 halves over 5 halves, plus 2 times x minus 1 to the 3 halves over 3 halves. So these are some basic things that we already know about antiderivatives. Namely how to do substitution and several of the rather simpler antiderivatives. The first technique here is called integration by parts. And if substitution was using the guess that there was a composition involved, parts is making the guess that there is a product involved with the integral. It's an attempt to use the product formula backwards, so that if we've got f times g of x, we take the derivative of this, it's f prime of x, first times the derivative of the second, or f times g prime of x, that's 5, plus the second times the derivative of the first. So the antiderivative of this, which ought to give us f times g again, you want f of x times g of x, should be this antiderivative plus this antiderivative with respect to x. Now the way this is used is as follows. If you've got the antiderivative of f times g prime, f of x times g prime of x dx, that's this. This is equal to f of x g of x minus the antiderivative of f prime of x g of x dx. Now what this does is the following. It takes a particular antiderivative that you're looking at it, and it changes it to a different problem. If the different problem is easier, or you can somehow get a hold of it, then you can solve the original one. So what this does, the anti-differentiation by parts, really changes the problem to a different one. Now, people like to think of this in several ways. One of them is this. If you let f of x be equal to u, and g prime of x dx be equal to the dv, that's to say, if we let v be g of x, then dv is going to be g prime of x dx, and f prime of x dx will be equal to du. Right? You can then write this formula as follows. The antiderivative of u dv is equal to v times u minus the antiderivative of v du. And in order to accomplish this type of thing here, it's convenient to do one of two things here. If you want to use the u and the v, make a chart here that consists of this. You've got u here and dv here. That's the first part of the integral. Then you've got du and v here. In forming this chart, you don't have to worry about the constants of anti-differentiation. You can add those at the end. But what the chart indicates is the following, that the antiderivative of u dv is this diagonal, u times v minus the antiderivative of v du. That's the same chart with the functions f and g prime looks like this. F prime, g prime, g. And what you've got is the following. The antiderivative of the top line here, that is the diagonal minus the antiderivative of the bottom line. So if you fill this in with f and g prime, or u and dv, then you find f prime and g, and you can then write this formula out like so. Now, one thing to note here is that whatever you pick for g prime, you have to make sure that you can anti-differentiate it, because you have to know the antiderivative of the g prime. Let's take a look at a simple example for starters here. Let's look at the antiderivative of x e to the x dx. And here I'm going to let x be f and g prime be e to the x. And consequently f prime is going to be 1, and g is going to be equal to e to the x. Right? And the nice thing about this here is that I've been able to fill in the chart, but I can also look on the bottom line and notice that I can anti-differentiate that product 1 times e to the x. So this antiderivative here is going to be equal to this diagonal, x e to the x, minus the antiderivative of e to the x. So this is going to be x e to the x minus e to the x plus any constant. Right? If you were doing this with u and v, you'd let u be equal to x, dv be equal to e to the x dx. du is going to be 1 dx, and v is going to be e to the x. And then this keeps, the differential should keep track of the whole picture here. X e to the x dx is the first integral. That is equal to x e to the x uv minus antiderivative of e to the x dx, e to the x times dx over here. So in either case here, you get this picture right here. And the antiderivative of x e to the x is as follows. Sometimes anti-differentiation by parts can be achieved by letting one of the parts be equal to 1. A couple of very important antiderivatives for that matter can be obtained in that fashion. Let's look first of all at the antiderivative of natural logarithm of x with respect to x. Well, here if we look at the integration by parts picture, and we let ln of x be our f over here, and f prime consequently is 1 over x, g prime, let it be equal to 1, so that g is x. We then find that the antiderivative of ln of x is equal to x ln of x minus the antiderivative of the bottom line here, which is 1 with respect to x, so that we get the antiderivative of ln of x is x ln x plus, minus x plus any constant. And so there's the formula for the antiderivative of the logarithm. Another such example where 1 is one of the parts. Suppose we want the antiderivative of tangent inverse with respect to x. Well, if we put tangent inverse over here, the derivative of tangent inverse is 1 over 1 plus x squared. If we put 1 over here, antiderivative of 1 is x. So here's f g prime, g, and f prime. So the antiderivative of f times g prime is equal to tangent inverse of x times x, or x tangent inverse of x, minus the antiderivative of the bottom line here, x over 1 plus x squared dx. But now this looks like f prime of x over f of x. It would be if this was a 2 up here. We can put a 2 in there and a half outside the integral and not change anything, and so that we then get that this is equals to x tangent inverse of x minus 1 half. Now this is f prime of x over f of x, so we get the log absolute 1 plus x squared plus any constant. So there then is the antiderivative of the tangent inverse function. And it's not worth remembering, but it's worth remembering that you can get it by means of anti-differentiation by parts with one of the parts equal to 1. The arc secant and the arc sine you can also find their antiderivatives by using one of the parts equal to 1. Let's take a look at them. Antiderivative of sine inverse of x with respect to x. Well, let's put sine inverse of x here and 1 here. Derivative of sine inverse is 1 over square root 1 minus x squared. Antiderivative of 1 is x. And so that this integral is equals to the product on this diagonal, x sine inverse of x minus the antiderivative of the bottom line here, which is antiderivative of x over square root 1 minus x squared dx. Now here, if we let, for example, u equal 1 minus x squared, right, du is going to be 2x dx, and this substitution right here is going to give us for this integral the integral of square root of u. X dx is du over 2, so du and a half. So we're going to get 1 half. This is u to the minus 1 half here, so the antiderivative is going to be u to the 3 halves over 3 halves. And now u was 1 minus x squared. So that this part right here is this, and so that the total antiderivative of sine inverse is going to be equals to x sine inverse of x 2/3, 3 halves, 2/3 up here, so we're going to get, so minus 1/3 on the minus side, 1 minus x squared to the 3 halves plus any constant. So there it is right there, the antiderivative of the sine inverse. All right, let's take a look at the antiderivative of the secant inverse. Right, here again we want to let one of the parts be 1, the other one be secant inverse. Right? The derivative of the secant inverse is 1 over x square root x squared minus 1. I'm going to leave the absolute x out of the picture here. That's common to do and correct for it at a later date. Antiderivative of 1 is x. So I get that this antiderivative of secant x here now is antiderivative of x secant inverse is x secant inverse of x secant inverse of x minus the antiderivative of the bottom line, which is antiderivative of 1 over square root x squared minus 1 dx. Now to get this second antiderivative here, a substitution which will become more familiar can be made here. That's to say, you'd like to see this look like secant squared minus 1, so that you'd get square root of tangent squared. So if I let x equal secant theta, and dx then becomes secant theta tangent theta d theta, then this becomes, this integral right here becomes integral dx is secant theta tangent theta d theta, x squared minus secant squared minus 1 is tangent squared. Square root of tangent squared is going to be tangent. Right? And so now what we're left with here is the secant of theta. Well, the antiderivative of secant theta is log absolute secant theta plus tangent theta. Right? And now theta was the secant inverse of x. So what we get here is that this integral here is x secant inverse of x minus log secant of secant inverse of x, which is going to be log of x, and then we've got plus tangent of secant inverse of x. Now this looks bad, perhaps, as an answer here. The tangent of the angle whose secant is x, however, can be simplified. If theta is the angle whose secant is x, then this is x to 1, and so this is square root x squared minus 1, and so that the tangent of the angle whose secant is x is square root x squared minus 1. So we can replace this right here with square root x squared minus 1 and get the antiderivative of the secant inverse is x secant inverse of x minus the logarithm of x plus the square root of x squared minus 1. Okay, let's take a look at some additional ones involving parts. These are frequently the type of things that you come to recognize. For example, if we have x cosine x dx, it's kind of clear we're dealing with a product here. And to find the antiderivative, we can certainly try integration by parts. In this case here, if we let f of x be equal to x, and g prime be cosine x, then g is sine x, and f prime is 1, and we can see that we can anti-differentiate the bottom line here. So this is going to be equal to x sine x, the diagonal here, minus the antiderivative of sine x, which is going to be equal to x sine x, minus the antiderivative of sine x is going to be minus cosine x, so plus cosine x plus any constant. So there's the antiderivative then of x cosine x. Do another one here. X squared plus 3x, say, times e to the x with respect to x. This is going to illustrate the possibility that sometimes you want to use parts more than once. Let's put x squared plus 3x over here, because when we differentiate it'll be simpler. and e to the x over here. We get then e to the x. We get 2x plus 3 down here. And we consequently get that this is equals to x squared plus 3x times e to the x minus the antiderivative of the bottom line. 2x plus 3 times e to the x dx. Right. To get that last integral here, we can use parts again. Right. We put 2x plus 3 e to the x here. We're going to get 2 and e to the x here. And so this is going to be equal to x squared plus 3x e to the x minus, now this antiderivative is going to be 2x plus 3 times e to the x, diagonal, minus the antiderivative of the bottom line, which you can just write in. The antiderivative of 2e to the x is 2e to the x. So this then plus any constant. And from this it's clear that if you've got any polynomial in x times e to the x, that you can find this antiderivative using parts like this. In fact, if you've got a polynomial in x times e to the kx, integration by parts will get you to the antiderivative. You may have to do it several times, however, depending on the degree of the polynomial, because each time you do it, the degree is reduced by 1. So here are a couple of examples then, of additional examples of integration by parts. Integration by parts again has quite a few, it occurs quite a bit, and we could do tons and tons of examples of it. Let's do a couple more here that indicate some tricks that sometimes show up. Let's take a look at e to the x cosine x. And for this purpose here, let's put e to the x over here and cosine x here. Right. And then the derivative of cosine x is going to be minus the sine of x. We'll get e to the x down here. And we're going to get here, the antiderivative is going to be e to the x cosine x minus the antiderivative of the bottom line, so that's going to be plus the antiderivative of e to the x sine x dx. Right. Now it looks like we've changed the problem from e to the x cosine x to e to the x sine x, which we have. And proper integration by parts again is in order. Now, if you do the wrong thing here, you can just run this right backwards here so that you end up with the antiderivative of this as itself. Here, you don't want to undo what you just did here because parts can do that. You want to put e to the x here again and e to the x here and sine x over here and cosine x over here. And so we get that this is equal to e to the x cosine x plus e to the x sine x, right, minus the antiderivative of e to the x cosine x dx. Now it looks like we're in trouble here because we're back to e to the x cosine x. However, what we can do is we can collect this together with this one here on this side and get 2 of them, right? In which case we find that the antiderivative that we're interested in here is going to be 1/2 of this. So the antiderivative is going to be equal to the antiderivative of e to the x cosine x dx is going to be equals to e to the x cosine x plus e to the x sine x over 2. While we're there, we can also get the antiderivative of e to the x sine x. It's this minus e to the x cosine x. So the antiderivative of e to the x sine x dx is going to be equal to this antiderivative minus e to the x cosine x. So it's going to be e to the x sine x over 2 minus e to the x cosine x. I subtract an e to the x cosine x off of here. All right. So we have these 2 here. All right. If we didn't have them at this point, we would need them shortly because we want to try something a little bit more complicated still. Let's look at the antiderivative of x e to the x sine x with respect to x. And now since we have the antiderivative of x, e to the x sine x, let's be bold here and put x over here and e to the x sine x over here. And then when we differentiate, we'll get 1. When we differentiate, we'll get 1. And here we're going to get the first times the derivative of the second, e to the x cosine x, plus the second times the derivative of the first, e to the x sine x. The boldness is paid off because we know how to antidifferentiate both of these. And so this antiderivative then is going to be equal to x times e to the x cosine x plus e to the x sine x minus the antiderivative of the bottom line here. Well, the bottom line is the sum of these two antiderivatives. So we're going to get minus e to the x cosine x plus e to the x sine x over 2 plus e to the x sine x minus e to the x cosine x over 2. And this, of course, can be simplified because you've got this minus this, and so we're going to end up with e to the x sine x. So that this whole quantity right in here can be replaced with minus e to the x sine x. And so here's the answer for this antiderivative. This right here has been replaced with e to the x sine x. Okay. And we now want to take a look at antiderivatives of powers of trig functions and products of trig functions. In particular, we're going to take these in pairs. Sine and cosine go together as a pair, secant and tangent, and cosecant and cotangent. We want to take a look at now things of the form, antiderivatives of the form sine to the n of x, cosine to the m of x with respect to x, where n and m are two natural numbers. And in particular, there's going to be two different types of techniques for this. The first one is going to hold when either n is odd or m is odd. So when either of the two of these are odd, then there's going to be one technique for finding the antiderivative. Let's take a look at how that goes. Let's take a look at the antiderivative of sine cubed of x, cosine to the fourth of x, dx. So that here the sine is odd. Well, the thing to do then is to save one sign and change everything over to cosines using the fact that sine squared plus cosine squared equals 1. So we save one sine of x, and we change the other sine squared into 1 minus cosine squared. So we end up with 1 minus cosine squared times cosine to the fourth with respect to x. And now if we let u equal cosine x, du is minus sine of x dx, and this is going to become a polynomial on u. That's to say this is the antiderivative of sine of x dx is minus du. And now here we've got 1 minus u squared times u to the fourth du, which is going to be minus u to the fourth. The antiderivative of that is going to be minus u to the fifth over 5. And we're going to have a plus u to the sixth. The antiderivative of that is going to be plus u to the seventh over 7. And now u is cosine x. So there's the antiderivative. Okay, let's look at something like the antiderivative of sine squared of x cosine to the fifth of x dx. In this case, the cosine is odd, but it's a very similar situation here. Right? That's to say, we save a cosine, right? And we change everything else to sine. So we can have sine squared And now cosine to the fourth, well, cosine squared is 1 minus sine squared. So cosine to the fourth is that squared. Now here, if we let u equal sine x, du is cosine x dx, and we get here that this is the antiderivative of u squared times 1 minus u squared squared du. And now this is just a polynomial, and you multiply it out, and you can antidifferentiate it. In the case that you've got, let's say, both powers odd, it doesn't matter what you do as far as saving something. You can either save sine x, for example, and do this as sine x. Sine squared is 1 minus cosine squared. So we get this times cosine cubed of x dx. And now u is equal to cosine x du is minus sine x dx. We find that this is equal to the antiderivative of sine x dx is minus du, so we get minus here du. Then this is 1 minus u squared times u cubed. And that's a polynomial in u. The antiderivative is easy. And then you just make the substitution back. U equals cosine x. Okay. So, the only thing left to note here is that one can also do these if there's no sine term or no cosine term. So that, for example, we can find the antiderivative of cosine x to the 5th power. The cosine is to an odd power here. So what we do is we save 1. Cosine x, and change everything else over into sines. So we've got cosine to the 4th is going to be 1 minus sine squared x squared dx. And now here, if we let u equal sine x, du is cosine x dx. We find that we're looking at the antiderivative of 1 minus u squared squared du. Which of course is going to be what? The antiderivative of 1 minus 2u squared plus u to the 4th du. And the antiderivative is going to be u minus 2u cubed over 3 plus u to the 5th over 5, and u is sine x. So there's the antiderivative, plus, of course, any constant. Likewise, for example, the antiderivative of sine cubed of x dx. If we save one of them, sine x, we change the sine squared over to 1 minus cosine squared. We get this like so, dx. Right? Now if we let u equal cosine x, du is minus sine x. And this becomes the antiderivative of minus 1 minus u squared du. So odd powers of sine or odd powers of cosine are products of sine and cosines to powers where one of them is odd. Can always be done by means of this technique here. All right, we're going to take a look now at antiderivatives of the form sine to the n of x, cosine to the m of x, where both m and n are even. Right, the previous example shows how to do this when one of them is odd, and we want to know what to do if both of them turn out to be even. Right? And the thing to do with this is to use the following identities. Cosine squared of x is 1 plus cosine 2x over 2. And sine squared of x is 1 minus cosine 2x over 2. These two trig identities will allow you to get rid of the even power here. And you may have to use them several times to get rid of it completely. But they will do the trick. So that, for example, if we wanted the antiderivative of sine squared of x, or of cosine squared of x with the same technique here, we would say, okay, this is equal to the antiderivative of 1 half minus 1 half cosine 2x dx, which is going to be equal to antiderivative of a half is 1 half x minus a half antiderivative of cosine 2x. Sine of 2x is a pretty good guess. The derivative is cosine 2x times 2, so if we divide this by 2, we'll be right. So that plus any constant. So here's the antiderivative of sine squared. Cosine squared would be similar. Let's see what happens. We've got something more complicated. Let's look at the antiderivative of cosine to the fourth of x times sine squared of x dx. Right? Well, we want to write cosine squared as 1 plus cosine 2x over 2. So we have this squared times 1, sine squared is 1 minus cosine 2x over 2. So we want the antiderivative of this with respect to x. Okay, well, we get a quarter out of this whole picture here, an eighth actually. I'm squaring all the 2's here, we get an eighth. And then we've got antiderivative of 1 plus 2 cosine 2x plus cosine squared 2x times 1 and then times minus cosine of 2x. So we've got minus cosine 2x minus 2 cosine 2x squared, right? And minus cosine 2x cubed dx. So that all of this belongs inside the dx here, huh? Well, let's do what we can with this. We have 1/8. Antiderivative of 1 is x. Antiderivative of 2 cosine 2x. Well, we've actually got 2 cosine 2x minus a cosine 2x here. So that's only 1 cosine 2x. So the antiderivative here is going to be equal to plus the antiderivative of cosine 2x. Sine of 2x over 2, huh? Sine of 2x would give you cosine 2x times 2, so half of that. Now we've got minus the antiderivative of cosine squared and we've got minus the antiderivative of cosine cubed of 2x dx. Both cases of 2x. That's all multiplied by an eighth. Now, for the cosine squared of 2x, here we want to use this again. Let's just say we're going to have, this is 1/8, x plus sine of 2x over 2, minus, cosine squared is going to be 1 plus cosine, now 4x, huh? Cosine squared of 2x is going to be 1 plus cosine of 4x over 2. Now this is cosine cubed. So we want to do this as a cosine cubed. So we want to save cosine of 2x and change the cosine squared into 1 minus sine squared of 2x dx. All right. On this we want to let u equal sine of 2x, in which case du is equal to 2 cosine 2x, and this becomes the antiderivative of 1 minus u squared. 2 cosine 2x dx is du, so cosine 2x dx is du over 2. So 1/2 du minus, that's this, The antiderivative here we can do at this point. We end up with minus a half x, and we've got minus a half. We want an antiderivative of cosine 4x. Antiderivative of cosine 4x. Sine 4x is a good guess, I guess, but it's off by 4. 4 times too large, huh? Derivative of sine 4x would be cosine 4x times 4. So sine of 4x divided by 4. So we end up with 1/8 x plus sine 2x over 2 minus a half x minus this and so forth here. And now we're almost home here, right? 1 minus u squared du. The antiderivative is going to be u minus u cubed over 3, and u is sine of 2x. We've got a half multiplying this. And here we've got an 1/8 sine of 4x. And it's a minus a half multiplying it, so this is going to be minus and then plus. And then we've got x minus a half x is going to give us a half x. We got sine of 2x over 2, and an 1/8 multiplies this whole thing. At any rate, the consequence is that if you get even powers of the cosine, you can use this substitution here, and every place when you use the substitution, you multiply things out. If you get odd powers, you already know how to do them. If you end up with even powers again, like here we ended up with cosine squared, then you use the substitution again until you have no more even powers and you found the antiderivative. All right, we now want to take a look at products of secants and tangents to powers. And cosecants and cotangents will be similar. And particularly, we want to look at antiderivative secant to the m of x, tangent to the n of x with respect to x. And here the case is going to be that if the secant is to even power, or the tangent is to an odd power, then there will be an easy way to do the problem. Secant is to even or tangent is to odd. The same thing will hold here if we've got cosecants and cotangents. If cosecant is even or cotangent is odd, the exact same thing happens except that you get some minus signs and some cos that you don't have otherwise. Let's take a look at an example. Antiderivative of secant to the 4th of x, tangent squared of x dx. Now the secant here is even. Right? So what we do is we save the derivative of the tangent. Right? That's to say secant squared. And change everything else over to tangents. So the other secant squared becomes what? Tangent squared plus 1 is secant squared. So this becomes tangent to the 4th plus tangent squared. Multiplying the tangent squared plus 1 by the tangent squared, like so. And now if you let u equal tangent x, du is secant squared x dx, and this becomes u to the 4th plus u to the 5th. I'm sorry, u to the 4th plus u squared du, and the antiderivative of that is u to the 5th over 5 plus u cubed over 3 plus any constant, and now u is tangent x. So if the secant is the even power, you save the secant squared and change everything else over to tangents. If the tangent is to an odd power, let's say antiderivative of secant cubed of x tangent to the 5th of x dx. Right? If the tangent is to an odd power, then you save a secant times tangent, the derivative of secant. If both of them are right here, like if the tangent is odd and the secant is even, then you can do it either way. But here you save a secant times tangent. So we end up with, all right, secant squared. Right? We end up with tangent to the fourth. We want to now change this all over to secant. Because we're going to have the derivative of the secant here. We're going to have everything else in terms of secant. So tangent to the fourth is tangent squared squared. And tangent squared is secant squared minus 1. So we've got this dx. And now we let u equal secant x. du is secant x tangent x dx. And this then becomes here's du. And we've got u squared times u squared minus 1 du, which is u to the fourth. Antiderivative of u to the fourth is u to the fifth over 5. Minus u squared, the antiderivative of u squared is u cubed over 3. And now u was secant x. So that plus any constant is the antiderivative there. Now, thing to note is this, that if the tangent is not around at all, and you have got the secant by itself to an even power, you can still use this method to do this. Let's take a look at, for example, the antiderivative of secant to the fourth of x dx. Right? Well, what do we want to do here? There's no tangent term here, so we want to change this as follows. Right? This is take a factor secant squared of x out of here, and change everything else to tangent. So we've got secant squared. It's 1 plus tangent squared. Right? And now we let u equal tangent x. du is secant squared. And this becomes antiderivative of 1 plus u squared, secant squared dx is du. So this is du, which is going to be equal to u plus u cubed over 3, and now u is tangent x. So if you've got the secant to an even power and no tangent term there, you can still do this. If you've got secant to the 0 power, that's to say it's not there at all, and tangent to any power, you can do this. So that, for example, if you want the antiderivative of tangent to the fourth of x dx, okay, if we change this to 1, tangent squared is secant squared minus 1. This squared dx. Right? We're going to end up with all powers of secants here. And so consequently, we're going to be able to do this just like we could do secant to the fourth here. Well, let's look at this. We're going to end up with secant to the fourth of x minus 2 secant squared of x. Okay, this is clear here, plus 1, huh? We just did secant to the fourth, no problem with that. The antiderivative of secant squared is tangent, and we can do the 1 here like so. Right? Tangent to the fifth, same situation. For tangent to the fifth of x, right? Save a tangent, and change the rest to secants. You will then have tangent to an odd power and secants. We're going to have secant squared of x minus 1 squared. We're going to have tangent to an odd power, namely 1, and secants. And so you can always do tangent to an odd power and secants. So here this indicates that, right, if you get an even power of the tangent, no secants there at all. When you change it over, you're going to get all even powers of secants, which you can do. That's when you've got an odd power of the tangent. If If you save one of them, you're going to end up with an odd power of the tangent in secants, and you can do that too. So, the tangent is odd, all right? You can always solve the problem. Generally, if there's secants involved, you factor out a secant times tangent. If the secant is even, you can always solve the problem. You factor out secant squared and change everything else over to tangents. Right? The exact same thing here happens with the cosecant being even and the cotangent being odd. Exact same thing, except that you're dealing with cofunctions rather than the functions. All right, we want to take now a look at secant, the antiderivative of secant to the m of x tangent to the n of x with respect to x, where m is odd and n is even. So that the previous thing that we've just done can't be done. Right? This will also work for the cosecant and cotangent. And the approach that's taken to this is to change everything over to secants. Since n is even, we'll change everything over to secants. And what happens then is we end up with powers of secants to deal with. Let's take a look at an example. We've got the antiderivative of secant cubed of x tangent squared of x with respect to x. This is going to be antiderivative of secant cubed. Change all the tangents over to secant, so this is going to be 1 minus, tangent squared is secant squared minus 1. Multiply it out, and we find that we're dealing with antiderivative of secant to the fifth minus the antiderivative of secant cubed. Right? So what we end up with is odd powers of the secants if you do this. Let's look at another one. Let's take a look at the antiderivative of secant to the fifth of x tangent to the fourth of x dx. Huh? We've got secant to the fifth of x. We change the tangent to the fourth all over into secants. So we have secant squared of x minus 1 quantity squared dx. This gives us secant squared secant to the fourth minus 2 secant squared plus 1. So when we multiply this out, we're going to end up with secant to the ninth minus 2 secant to the seventh plus secant to the fifth. So it's clear that what happens here, you've got an even power of tangent along with secants. If you change it over to secants, you're going to end up with all odd powers of secants. And what we want to know is then how to do odd powers of secants. And then the problem of secant times tangent will be solved. Cosecant, cotangent, similarly. We now want to take a look at the antiderivatives of odd powers of the secant. All right. Well, the antiderivative of the secant of x to the first power dx is log absolute secant x plus tangent x plus any constant. Huh? You can check this very easily by differentiating. Here we're going to get secant x plus tangent x, 1 over secant x plus tangent x. If we differentiate this, times the derivative of secant plus tangent, derivative of secant is secant tangent x. Derivative of tangent is tangent squared. Right? And the tangent squared. Secant squared. Secant factors out of here, leaving you with secant x. Secant factors out of here, and you end up with secant plus tangent over secant plus tangent times secant. So secant x. So here's secant to the first power, which is a start here, huh? We want now the antiderivative of secant cubed. Huh? And all of these antiderivatives involve using the following trick here, so to speak. You put secant squared over here on the right-hand side, and you do this by parts. Right? So we end up with secant over here and secant squared over here. All right. The antiderivative of secant squared is, of course, tangent. And the derivative of secant is secant times tangent. So the antiderivative of secant cubed is going to be equals to secant x tangent x minus the antiderivative of the bottom line here, which is secant x times tangent squared. And now tangent squared, I'm going to change to secant. So that's tangent squared is secant squared minus 1. So this is times secant squared minus 1, or secant cubed minus secant. And secant times secant squared minus 1. Now, it looks like we're in trouble here, but not so. We've got another secant cubed here. We get secant x tangent x. All right, the antiderivative of secant x we already know here. So we have plus the antiderivative of secant x, which is log secant x plus tangent x. Now we got another secant cubed here. We'll bring that over to this side. We'll have two of them and divide by 2. So the antiderivative of secant cubed is secant x tangent x plus log secant plus tangent over 2. So that gives us secant cubed. Right. Take a look at secant to the 5th. You see there's a pattern here. And in fact, there is a formula that's given in a good number of integral tables that shows you how to reduce odd powers to lower ones here so that you can finally end up with a formula. Once you've got secant cubed, we're going to be able to get secant to the 5th with the same procedure here. Put secant squared here and integration by parts so that we get tangent here. And over here we're going to get secant cubed. And for the derivative of secant cubed, we have got 3 secant squared times the derivative of secant squared times the derivative of secant, which is secant times tangent. So we're going to, altogether we're going to have 3 secant cubed tangent. These are the parts. And this becomes antiderivative of secant to the 5th is equal to secant cubed tangent x minus the antiderivative of the bottom line minus 3 antiderivative. We've got secant cubed here. We've got tangent squared. We're going to change the tangent squared to secant squared minus 1, giving us secant to the 5th minus secant cubed. So that line right there is secant cubed times secant squared minus 1, or secant to the 5th minus secant cubed. Okay, we already know secant cubed. It's right up here. So if you want here, this is secant cubed tangent x minus plus, I guess, 3 times the antiderivative of secant cubed here. That's going to be this over 2 here. Secant x tangent x plus log absolute secant x plus tangent x over 2. Right? That takes care of this and this. Now we've got 3 secant to the 5th here. We bring them over to the right-hand side. We have 4 of them all together. And so that if we divide this by 4, we get the antiderivative of secant to the 5th. Now, of course, this could be simplified a bit. Okay. Antiderivative of secant to the 5th is this, plus any constant. And from there you can get the 7th and the 9th and however high power you wish. We going to look at now technique is called partial fractions. What it is a technique for dealing with all rational functions. Let's say functions of the form p of x over q of x, or p of x and q of x are polynomials. The first thing you want to do with, if you've got something of this form, antiderivative p of x over q of x with respect to x, is to make sure that the numerator is of degree lower than or equal to the denominator, and you can always do this by dividing the denominator into the numerator. So that, for example, if we have something like the antiderivative of x to the fourth plus 7 over x squared minus 1 dx. The numerator is of higher degree. Even if it was equal degree, we could take x squared minus 1, the denominator, and divide it into the numerator, getting x to this into x to the fourth plus 7 is going to give us x squared. We end up with x to the fourth minus x squared. Subtracting, we get plus x squared plus 7. Dividing here, we get plus 1. We get x squared minus 1. Subtracting here, we're going to get 7 minus a minus 1 is 8. So that this integral right here is equal to the integral of x squared plus 1. We've got a remainder of 8 here, so we have plus 8 over x squared minus 1. You can always continue dividing here until you have got a remainder which is of lower degree than the polynomial you're dividing in. And so you can always reduce this problem to one where you've got a polynomial, which you can do easily, and a rational function where the degree p, the numerator, is less than the degree of the denominator. Right? Now, the next thing to do here is this. We claim that we can write this antiderivative of x squared as x cubed and over 3 plus the antiderivative of x of 1 is x. And now the claim is we can write this as a over x minus 1 plus b over x plus 1 for appropriate choice of a and b. In particular here, x squared minus 1 factors into x minus 1 and x plus 1. And when you've got such a factorization into monomials, you can then always write the fraction with the numerators of lower degree as a over one factor plus b over another factor. If they're repeated factors, you have to include them too. We'll take a look at that. If we knew this, we would then write that this is equal to x cubed over 3 plus x plus antiderivative of a over x minus 1 is going to be a log absolute x minus 1. Antiderivative of b over x plus 1 is going to be b log absolute x plus 1, and so we would be done. Right? To see that we are, all we want to do is to look at this, to put these over the common denominator x squared minus 1, and write 8 equals a times x plus 1 plus b times x minus 1. These would be the numerators if this was put together over the common denominator x squared minus 1. This side we would want 8, here we would have this. Right? Now the way to do this actually is to solve for a and b here by writing the equation that you get when you equate the constant coefficients, so that, for example, 8 is equal to 1a minus 1b, and the x coefficients. On this side there's none, and 0 is going to be equal to, consequently, a plus b. Right? If we solve these two equations and these two unknowns, we can find out what a and b are. Right? If we know, however, that this is going to work, and we'll assume that it will, you can always check it. You can frequently put in a number for x and find out what a and b are. So in particular, if I let x equal 1 here, the b disappears, and I get 2a is equal to 8, so that a is 4. So I automatically know what a is 4. Right? And if I let x equal to minus 1 here, this part disappears. It's 0, that is to say, we get minus 2b is equal to 8. So the b is minus 4. So we get minus 4 here. And that tells me what A and B are. We've now completed the integral of this quantity right here. Namely, it's this. Let's try a different one here. Let's take a look at the integral of x squared minus 2x minus 1 over 2x plus 1 times x minus 3 times 3x plus 1 dx. And the numerator is of lower degree than the denominator. So what we want to do with this is to write it as antiderivative of a over 2x plus 1 plus b over x minus 3 plus c over 3x plus 1 dx. If we can do that for a, b, and c, and it's an algebra result that says that we can here, then we can antidifferentiate this very easily, because this then is equal to a over 2x plus 1. That's going to have this antiderivative a log 2x plus 1. Well, not quite, huh? Over 2. Plus b log absolute x minus 3 plus c log, we have 3x plus 1 here, so it's going to be 3x plus 1 over 3. Now, to find out what a, b, and c are here, we really want to compare x squared minus 2x minus 1, and what we get if we put this over the common denominator. This is a times x minus 3 times 3x plus 1 plus b times 2x plus 1 times 3x plus 1 plus c times 2x plus 1 times x minus 3. Now, watch what happens here. You can either get yourself 3 equations and 3 unknowns by comparing the x squared coefficient to the x squared ones on the right here. That'll give an equation in a, b, and c. The x one to the x's on the right, and the constant to the constants on the right. Or, assuming that you're going to be able to do this, you can, for example, let x equal 3 in here. This will drop out when x is 3, and this will drop out when x is 3, and you will get the b's term. So when x is equal to 3, we will find the b's term. It will be 2 times, we'll get an equation for the b's term. We're going to get x squared here, which is 9, minus 6 minus 1 will be equal to 7b times 10. So that 9 minus 6 is 3, minus 1 is 2, is 70b. b is 2 over 70. If we let x equals to a third, minus a third, this will drop out, and this will drop out, and you have an equation that will give you the c term. If you let x equal minus a half, this right here will drop out, and this right here will drop out, and you have an equation that will give you the h term. So you get the c term and the h term here in that fashion, or you can solve the 3 equations and 3 unknowns that tell you how the coefficients are related. The x squared coefficient here is 1. On this side it's a times 3, and b times 6, and c times 2. That gives you 1 is a plus 6b plus 2c. You get 3 equations and 3 unknowns, and you can solve them. Okay. Okay, we want to take a look at partial fractions some more here to get all possible cases under control. The situation is this, that there's a theorem that says that any polynomial of no matter what degree can be factored into polynomials of degree 1, monomials, and polynomials of degree 2, which can be no further factored. Now, we're going to assume that we can do some sort of factorization like that from the standpoint of finding the antiderivatives in here. So that first we're going to still consider the situation where the denominator is factored into polynomials of degree 1. So, for example, if you have 3x squared plus 7 over x minus 1 squared times x plus 3, we want the antiderivative of that with respect to x. Right? Now, the algebra result says here, that since this is of lower degree than the denominator, we can write the denominator here as a over x plus 3 plus b, and now we have to consider x minus 1 squared and also x minus 1, so x minus 1 like so. Antiderivative of this with respect to x. If this was the cubed power here, we'd have to consider the cubed and the squared of the first power, with the a, b, and c are 3 different constants above each. If this was cubed and this one was squared, you'd have to consider the cubed at all lower powers and the squared at all lower powers. But if we can get this in this form here, there's no problem solving this anti-differentiation problem. What do we need at this point? We need to write 3x squared plus 7 equals a times x minus 1 squared plus b times x plus 3 plus c times x minus 1 times x plus 3. Right? Now here you can, as always, you can solve for a, b, and c by comparing the squared x and its coefficient. Powers are higher. Over here, you compare the higher coefficient. It's easy to get several of these things almost for free. If we let x equal 1, for example, we get on the left-hand side here 3 plus 7 is equal to, here we get 0, here we get 4b, and here we get 0. So we get 4b is equal to 10, b is equal to 10 over 4, or 5 halves. Likewise, if we let x equal minus 3 here, we get 27 plus 7 is equals to minus 3. We get 16a, we get 0b and 0c. So we got 34 is equal to 16a, or a is equal to 34 over 16, or 17 eighths. Huh? So this gives us a is 17 eighths. Right? Now that's the only thing we're going to get for free. We're going to get 2 of these things for free, but we need c. Well, we can get c in a number of ways. Probably the easiest is to compare the x squared coefficient. The x squared coefficient here is c. This doesn't have 1. The x squared coefficient here is a. And the x squared coefficient over here on this side is 3. So c is equal to 3. Oops, this is plus. C is equal to 3 minus a. A was 17 eighths. 3 is 24 eighths. So 7 eighths should be C. All right. Assuming no errors have been made, those should be the constants up here. And now the antiderivative is going to be equals to what? 17 over 8. Antiderivative of 1 over x plus 3 is log absolute x plus 3 plus 5 over 2. The antiderivative of x minus 1 to the minus 2 is x minus 1 to the minus 1 over minus 1. Right? If there was a constant in here, you'd have to adjust for that, but there's no difficulty anti-differentiating 1 over ax plus b to a power. The antiderivative of 7 eighths, 1 over x minus 1, is log absolute x minus 1. So here then is the answer to this problem here. All right. Now, I want to take a look at what happens in certain circumstances here. Suppose we have something like the antiderivative of 3x cubed plus 7x squared over x squared plus 1 times x minus 1 squared dx. X squared plus 1 cannot be further factored. But the algebra theorem says that we can write this as follows. This is of lower degree than the denominator. The denominator's got degree 4 here, x to the 4th, and this is x cubed. The algebra theorem says that we can write this as, for this term that can't be further factored, we can put ax plus b in the numerator and it in the denominator. Then we also need this x minus 1 term here. And since this is to the second power, we're going to need c times its squared plus b over it to the first power. These we can do easily. We'll take a look at how to do things that look like this. And then you'll be able to do things that are this fashion. Right? If you had something like 4x to the 4th plus 7 over x squared minus 2x plus 7 squared, let's say, times x plus 1. Now you've got a polynomial here of degree 2 that can't be factored, but you've got it to a power. Right? The algebra theorem says this. This is to a lower degree. You can write this as ax plus b over this squared, x squared minus 2x plus 7 squared, plus cx plus d over it to the first power. Right? Then we've got this x plus 1 here, so we need plus e over x plus 1. Now we want to see how to do this type of thing here, and then we'll be able to do this type of partial fraction. Right? If this was to the third power, you'd have to have a linear part over the third power, another linear part over the second, and another linear part over the first. Okay, so this is simply a question of writing out the equations and solving for a, b, c, and d, equating this to that over there. Similarly here. So we can assume that we can do this at this point, and we then wish next to take a look at, okay, how do we handle this type of thing here? And how do we handle this type of thing here? Okay, we now want to take a look at a specific type of partial fraction. This is what things can be decomposed down to. We'll see shortly. We want to look at something in the form ax plus b over x squared plus 1, respect x. If we have something that's strictly in this form here with x squared plus 1 in the denominator, then we can rewrite this as ax over x squared plus 1 plus b over x squared plus 1 and now this is almost f prime of x over f of x. In fact, if we put a 2 up here and a half in front, we would have f prime of x over f of x. We find that this is equal to 1/2 a log of x squared plus 1. That's this right here. Now this is tangent inverse function. So this is plus b tangent inverse of x. So this plus any constant, and the problem is solved. That takes care of everything that can be done, that can be made to look like this. Now, we'll see that a lot of things can. But first of all, let's consider something slightly worse here that's going to show up in partial fractions form. Ax plus b over x squared plus 1 quantity squared. And on ax plus b over x squared plus 1 quantity cubed. If this was the specific polynomial in the denominator, we're going to have to deal with this type of thing here. Well, the way to deal with this is as follows. This is ax over x squared plus 1 squared dx b over x squared plus 1 squared dx. So you take the two parts like so. And now this almost looks like f prime of x, f of x to a power. Right? F prime of x, antiderivative of f prime of x, f of x to the n. Huh? If there was a 2x in here, it would be. In which case, this would be, if I put a 2 here and a half outside, I get a half a, and now the 2x makes this f prime of x, f of x to a power. So we're going to get x squared plus 1 to the next higher power minus 1 over minus 1. So that's that antiderivative. Now, what to do with b over x squared plus 1 quantity squared? The thing to do with this is to use the substitution. Let x equal tangent u. So we get tangent squared plus 1, which is going to give us secant squared. In that case, dx is equals to secant squared u du, and this becomes the antiderivative of b. We have tangent squared plus 1 is secant squared squared, so this is going to be secant to the 4th of u. In the numerator here, we're going to get dx is secant squared u du, so we get secant squared u du, and this now is equals to b cosine squared of u du, which is something that you can do. We've got the cubed power here to do the same type of thing. You write this as ax over x squared plus 1 cubed, or any higher power, and then this looks like f prime of x, f of x to a power, plus, now you have b over x squared plus 1 cubed, antiderivative this with respect to x. You make the same substitution here. So you let x equal tangent u dx equals secant squared u du. You're going to end up with secant squared over secant to the 6th here, which is going to give you cosine to the 4th. So in either case here, you can find an antiderivative of ax plus b over x squared plus 1 to any power. And this is going to allow you to complete the picture involving partial fractions. Now you can also find these antiderivatives in just about any table of integrals. All right. We now want to see how to make anything look like ax plus b over x squared plus 1 to a power. Even though it doesn't seem to look like it, but if it consists of ax plus b over a factor, a polynomial degree 2 that can't be factored to a power, we can make it look like this. Let's take an example. Minus 3x plus 4 over 5x squared minus 3x plus 2 dx, or parallel situation here, minus 3x plus 4 over 5x squared minus 3x plus 2. Let's imagine that this is now to the 3rd power here. Now, we can determine that the denominator here can't be factored, and we can write this then as, well, let's just consider 5x squared, I'm just looking at the denominator here, minus 3/5 x plus 2/5. Right? And when I complete the square here with this, I would divide this by 2, I'll get 3/10, and square that's going to give me 9/100. So plus 9/100 will make this a square. I got to subtract have to subtract 9/100ths over here. So I get this is equals to, the denominator here is equals to 5 times x minus 3/10 quantity squared plus, this is 2/5, so it's 40/100ths, so plus 31 over 100. The fact that this is the sum of two squares here indicates that it can't be factored any further. Now, the idea is to make a substitution here so that this looks like x squared plus 1, or u squared plus 1 if you want. So I want this to look like u squared plus 1. Right? Okay. If I simply let u be equal to x minus 3/10, then I'm going to get u squared plus 31/100ths, huh? So what I want to do is let square root of 31/100ths u be equal to x minus 3/10. Because then 31/100ths u squared will be equal to x minus 3/10 quantity squared. When I put this in here, this is going to be, if I make this substitution here, this is going to equal 5. The 31/100ths can be factored out, and I will have then u squared plus 1. U squared plus 1. And the 31/100ths is factored out. So that if you make this substitution right here, you end up with u squared plus 1 here instead of this. And here you end up with it squared, or cubed, if it's cubed. What else happens? Well, du is just 1 dx here. Or a constant times du is dx. So this doesn't change the situation in the numerator here. And then this u and is substituted for x up here, and you end up with a linear equation in the numerator, and so you end up with something of the form au plus b over u squared plus 1 after the substitution is completed. Right? And in this case over here, you end up with a cubed. So in either case, you can take something with a denominator can't be factored. It's of degree 2. It's of 2 power perhaps. The numerator is of degree 1, and you can always make a substitution here. This is an illustration so that after the substitution you have u squared plus 1 to a power in the denominator. And you'll have something that's linear in the numerator. Okay, I want to take a look at some substitutions now that sometimes will enable you to solve a particular problem or reduce it to one of the forms that we can already solve. Let's take a look at, for example, the antiderivative of the square root 4 plus x squared dx. Right. Here what you've got, we're going to look at right now are substitutions where you've got some sort of a square root of something here, and you can simplify it here if you make it worse. In particular here, if this looked like 1 plus tangent squared, the problem would go away. So that if we let x be equal to 2 tangent u, then we would get 4 plus 4 tangent squared, and our problems would be over, hopefully. Dx is going to be equal to 2 secant squared of u du, and this then becomes antiderivative square root 4 plus 4 tangent squared u times 2 secant squared u du. Right? The 4 can be factored out of here, leaving us with a 2, so we get 4. Along with that 2, We have 1 plus tangent squared, which is secant squared. So the square root of secant squared is secant. We have secant times secant squared, or secant cubed of u du, and that's something that you can know how to do. It's an odd power of the secant and can be done. Right. Let's take a look. So here, when you're looking at something that looks like 1 plus x squared, or square root of 1 plus x squared, tangent. That's 1 plus tangent squared. Let's look at the antiderivative of 1 over square root x squared minus 3 dx. Here you'd like this to look like secant squared minus 1. So that if I let x be equal to secant u, that's not quite right, huh? Right, then when I square this, I'm going to get secant squared minus 3. So let me make this square root of 3 secant u, so I get 3 secant squared minus 3. Then dx is equal to square root 3 secant u tangent u du. And this becomes antiderivative of square root 3, right? Well, what have I got here? Secant squared minus 1. Square root secant squared minus 1. Right? And in the numerator, I've got another square root 3. Secant u tangent u du. So the square root of 3's cancel here. Secant squared minus 1 is tangent squared. Right? Square root of tangent squared. We're going to write it as tangent. You have to watch the sign a little bit. But anyway, this can cancel with the tangent. And now we're left with the antiderivative of the secant. And so the problem is essentially solved. And here the situation here is, when you're looking at something like square root x squared minus 1, you'd like this to be secant squared minus 1. Right? The final possibility here is if we were looking at something like square root 1 minus x squared, and you'd like to make a sine substitution in here, or a cosine, since you have 1 minus sine squared, 1 minus cosine squared. Let's take a look at antiderivative 3 minus 2x plus x squared square root dx. Make this minus x squared. All right. So what have we got here? This is a minus x squared plus 2x, like so. If I complete the square here, I've got 3 out here. If I complete the square root here, I want to add 1, which is to say I subtracted 1. So if I subtract 1, I have to add 1 to get out of here. So that I've got the antiderivative, this is the antiderivative of this. That's to say, it's the antiderivative of 4 minus x plus 1 squared, square root, dx. And now this, I'm looking at something that looks like 1 minus x squared. I'd like to make a sign substitution in here. In particular, I'd like this x plus 1 to be equal to not sine u, but 2 times it, so that when I square it, I get 4. And so that dx is equal to 2 cosine u du, and this becomes then antiderivative of square root 4, which is 2. Now I've got 1 minus sine squared, which is cosine. And then I've got dx is 2 cosine u du. So I've got 2 cosine u du. And you end up with a problem of finding the antiderivative of cosine squared, which is doable. So when you've got things that look like this, the tangent, secant, and sine substitutions are frequently going to solve the problem, even though it looks like as if they're going to make things worse. Another miscellaneous substitution that sometimes works is something that looks like u to the n equals x. So that, for example, if you have something like 1 over x to the 1/2 plus x to the 1/4 dx. Right? Well, here we've got a 1/2 and a 1/4. If we had a 1/3 in here too, we'd let u to the 12th equal x here, but u to the 4th equal x. And then 4u cubed du is dx. And then this becomes equal to the antiderivative of, what have we got here? We've got x to the 1/2 is going to be u squared. And x to the 1/4 is going to be u. And in the numerator, we're going to have 4u cubed and du. And we've got a partial fractions problem now. You have to divide this into here. This factors into u times u plus 1, and the whole thing will be resolved. But if you had something like x to the 1/3 over 1 plus x to the 1/2, same story. Let u to the 6th equal x. Then 6u to the 5th du will be dx. And this will become equal to u to the 6th is x, so x to the 1/3 is u squared. 1 plus u cubed. And dx now is 6u to the 5th du. And it's, again, you've clearly reduced it to a partial fractions problem. Suppose you have something like 1 over x squared square root x minus 1. And I derivative of this with respect to x. Right. A slight variation here, all right? So we'd like to get rid of this square root x minus 1. Let's let u squared be equal to x minus 1. Then 2u du is equal to dx. Right? And what else do we get here? We get if u squared is x minus 1, then u squared plus 1 is equal to x, or x squared is equal to u squared plus 1 quantity squared. This becomes then antiderivative of square root of x minus 1 is u. X squared is u squared plus 1 quantity squared. And dx is 2u du. Huh? The u's actually cancel here. And you're looking at a partial fractions problem of a simple order. Okay, so u to the n equals x, or in this case, u to the n equals ax plus b. Sometimes, for that matter, u to the n equals ax plus b over cx plus d. Can simplify the given problem. Okay, we want to take a look at now the situation where you're looking at some sort of a rational function in sine theta and cosine theta, where instead of x's, there are sines and cosines of theta with respect to theta. And now there's really a systematic substitution here that will work on this and make it into, however messy, a partial fractions problem. And that substitution is to let u equal tangent theta over 2. So that theta is equal to tangent inverse u times 2. If we look at a triangle here, if this is the angle theta over 2, then u is tangent theta over 2, so we can complete this triangle here that looks like this, u and 1. The other side here is square root 1 plus u squared. So we get sine theta over 2 is u over square root 1 plus u squared. Cosine theta over 2 is 1 over square root 1 plus u squared. And now we want to know what to substitute for sine theta. Now, someone has worked this out here, and it's all going to work out fine here. Sine of theta, right, is 2 times sine of theta over 2 is sine of 2 theta over 2. Using the double angle formula here, this is 2 sine theta over 2 cosine theta over 2. So the sine of theta is sine theta over 2 cosine theta over 2 times 2, which is 2u over 1 plus u squared. So this is what you substitute for sine theta if you're making this substitution. Cosine theta is equal to cosine of 2 theta over 2. Cosine of 2 times an angle is cosine squared of the angle minus sine squared of the angle. Which, what? This is going to be, cosine squared is going to be 1 over this, over 1 plus u squared, and sine squared is going to be u squared. So you get 1 minus u squared over 1 plus u squared. So this is what the substitution is going to cosine of theta. All we need now is d theta.